I told you that the generator is, this is the algorithm of Dirac. The generator is just a linear combination of all the first class constraints of the theory, primary, secondary, tertiary, or anything. So if I form this generator, then this is just epsilon A by A.
Sir?
Where yes.
বলছি এটা মাইক্রোফোনটা লাগিয়ে দেবো তাহলে এটা
লাগিয়ে দাও
1 minute 6 minutes
So, power to put on. Good. Now you can hear me? Okay, so this is the algorithm of Dirac. States that the generator is a linear combination of all the first class constraints of the theory. But point is, I mean, this is just not enough. I mean, this will not give you the generator at the level of the action. So, as I told you, suppose you write an action which has a gauge invariant. I want to find out the appropriate generator. Then, only this we will do. Something more has to be done, and this was done by a discussion of it. You can find in the book by Title 1. It was a mathematical argument, and it was also done by us from a different point of view. And I will just discuss that. That is the approach which was developed by us, and how very economical and also very conceptually elegant. So, the action is written like this, LDT, and the point is that you have to rewrite this action in what's called the Hamiltonian phase space variables, and that is easily done by the appropriate Legendre transform. Pi qi dot minus h, that's the transient. But as I have told you that now we are working with the constraint systems. In constraint systems, this h gets replaced by what's called the total Hamiltonian. And the total Hamiltonian is the canonical part, and then you have what? You have the primary constraints. A1, the notation A1 is for primary and A2 is for secondary, tertiary, everything, and A includes both A1 and A2. So these are the Lagrange multiplier which enforces the primary constraint. Okay, so this is the action for a constraint system. So let me consider an infinitesimal variation of this. And then you can write this as this. Then this algebra is simple, but it's also slightly tricky, so you have to be a bit careful. This will actually write it this way, and then you can write this as a total derivative So I've subtracted one part of this, but the other part is just leaving like this. So, and this is the way you write it, and then you have to remember that these are the phase space variables, you see, these are the phase space variables. The variation has now just come on the phase space variables, and this is what? This is defined as this bracketing with the generator. This gives you the variation, and then you use the algorithm to write the generator as this, which is just this. And as I've seen, as I've told you, that this A includes everything, the primary and secondary all. So this you can rewrite it as epsilon A times this, and then we may write this as epsilon A, and this is minus. So I hope you understand this last line. This the constraint is just a function of the phase space variables Q and P, and bracketing basically means you're taking a partial derivative with respect to Q, and because P with Q is a minus of 1, the minus sign comes here. Okay. Well, the other term just drops out because as I've told you, if you take the bracket and the constant remains outside, you can ignore it. Okay, so this is delta Pi. And delta Qi can also be done exactly in the same way. And if you combine the two results, then this has the form this is the first one. And then I have this term. So here the sign doesn't change, it remains minus. And then you have the other terms. This is, and this is clear. Good. So we continue. Okay. Now you can rewrite that as follows. Phi A is function of Q and P. And you see it appears as del phi del Q Q dot. That's del phi del Q dot. That's basically phi dot. Okay? It's clear, yes? Good. So I have taken into account the first two terms, and then I write the last two terms.
Also the minus. Minus lambda Fi.
No, I made an error. This should be
That
plus.
should be plus, yes.
Okay.
Now you can write this as, so there's a dt always sitting outside. Then, so I have included one part of this, but I have something extra, and that's subtracted out. So is this clear? This term should be clear, yes? This is this term, but I've just rewritten this as two pieces, which are written here. And then I've just taken the variation and split out everything. So now you see I have to write phi. Yeah? It's not that I can just simply drop phi, no, it's no Poisson bracket or anything. So everything has to be retained. This is this. Now for invariance of the action, you can always drop this bound term. So you so this is gone. So if you want the invariance of the action, then of course, you see, this has to be written in a particular way. The integrand will be written in a particular way, and that will be set to 0. And that will give you certain conditions, and that's what we found. This is quite easily done. This part just stands out as it is written. And you can see for yourself that there's a special isolation of the primary sector. You can see that A1 has come out. Yes. So you have to actually write this as what? Epsilon naught A1 phi A1, and then you have epsilon naught A2 phi A2. You follow that notation. Yes. And then you have to now actually interpret these terms. So let me write them as follows. What is delta HC? This is actually the variation. So you have this is basically this thing, right? This is this. And delta of this one, delta of phi A1 okay, right? Now, you have what's called the closure of the first class algebra. This system is assumed to have only first class constraints, right? There are no second class constraints. If there are second class constraints, you have to first eliminate the second class constraints by using Dirac brackets so that there are no second class constraints. And then all Poisson brackets are appropriately reinterpreted in terms of the Dirac brackets.
Sir,
Yes.
sir, I have a question.
Yes.
Sir, you have told that the definition of the constant or like that the time derivative of the constant should be 0. And in the classes, previous classes.
What has this to do with the time derivative?
So the first term in the
First line.
This one?
yeah.
But I am not taking anything to 0 now. You see, because I want to find out a condition which will maintain the invariance. There is no harm if I keep a 0 here.
Okay.
So, but is there a statement akin to saying like phi dot should be 0 and Hamilton's equations are not quite at this level?
No, the point is that the phi dot is equal to 0 is a tricky statement. You have to be careful. Phi dot is equal to 0 doesn't mean that you can just ignore that particular term, because phi dot is equal to 0 has several possibilities. One possibility is a trivial possibility, in which case you could have blindly dropped it. 0 is equal to 0. But phi dot equal to 0 can give me other things. Even it can give me a new, and it does give me a new constraint. Okay? So I mean, you have to retain it. It's always useful to retain it. It is 0, but it is 0 only weakly 0. It's not strongly 0. Okay? And at this level, I would like to retain it because, as I told you, I'm now working out the things at a very strong level. Okay? So, for instance, even phi a is 0. This is 0. So, the constant is 0. But this is what? It's weakly 0. So, I'm not putting that equal 0. There are no, at this level, there are no brackets involved. But the moment you see, when I go to a level of a bracket, I'm actually putting it 0 because delta HC is HC bracket with the G. The generator is what? Epsilon A, phi A. We'll have two terms. I've written only one of the terms. The other term is what? It is HC epsilon A phi A. But that's at the level of the bracket and that's dropped. You don't drop that term out. Okay.
So the time derivative of the fast, the constant is weakly 0.
Yes, everything is weakly 0. Phi dot equal to 0 is not a strong statement. If it were a strong statement, then the constant that you generate from that would imply that that is strongly 0. But that, you see,
Yeah.
you get the point, but that is not correct. All constants are only weakly 0. Therefore, the statement that phi dot equal to 0 is only a weak statement. Okay, now this, what is the closure of the algebra? If this is a first class constraint and the algebra closes, means this will give me what? There will be some structural constants, so it will be something like A1A, B, phi B. This is what is meant by the closure of the algebra because this is first class. And similarly for this, right? When you take the bracket with the Hamiltonian, it must always give me something which is back to constant. Why? Because the total Hamiltonian is HC plus the primary constraint. And the constraint with the total Hamiltonian, the bracket, that's phi dot. That has to be proportional to a constraint. You get the point? Phi dot has to be proportional to a constraint. However, the total Hamiltonian comprises two pieces, the canonical part and the primary part. The primary constraint, well, rather, yes, the primary constraint part. Now, this with this is already proportional. Therefore, this also has to be proportional. You follow, huh? Therefore, this is the reason that with the canonical Hamiltonian also the algebra with the first class constraint closes. This is very important. So you have to now use these results here, and therefore I derive this delta HC by just replacing it by this. And likewise, I will also change this. There is a lambda 1, and then I just put this.
So, but then you're doing something like a non-shell action, right? I mean, you're putting in the equations of motion into the variation.
I have not put any equation of motion. Where?
I mean, for delta HC,
Where? This is not an equation of motion.
it's not an equation of
No.
motion, but it's the shell where phi is 0.
No. Where
Because
is phi 0? This is a strong equality. If phi is 0 means this is 0. No. This is neither an equation of motion and neither is it an on-shell relation. This is a property of the first class constraint of the theory. Unfortunately, this is the trouble because nobody ever taught you this. And you will never understand this theory if you don't understand constraints. Only very few people laid emphasis, the sole exception being the Russian group, and that is the reason the Russians have made such incredible advances in the quantization of gauge theories, which nobody else has done. The whole group, from starting with Faddeev to Fratkin to Fratkina to Batalin to Lukovisky, I mean, n number of people, all Russians. The reason is that they have laid great emphasis on the theory of constraints. And this, by definition, is a property of the constraint. There is no approximation, no on-shell, nothing. This is a first-class constraint property. This is the first-class constraint property. Okay, these are strong relations. Good. Now you see at this level, we have got this thing. So now we may rub this part out and concentrate on the integrand. And the integrand will be split into two pieces. One will be the primary sector and the other will be the secondary sector. On top of it, we assume here that the constraints are